Next speaker is Nathan Giles Donovon from where are you?
From University of Glasgow.
Up on the left. Okay.
Yes.
The right one is at the left. Okay, thank you. Okay, thank you.
Right. So I'm going to talk to you today about copper niobium oxide. So I'm going to start off just introducing you a bit to the material, and then we'll talk about the techniques that we use to study it, and then we'll present some results. So copper niobium oxide has room temperature symmetry P1 bar. You can see the structure here. Okay. So you have your inverter center here. These are the three coppers. And it undergoes two transitions upon cooling. The first one, the magnetic order turns on about 26.5 Kelvin, and then a polarization develops at 24. And the structure has been determined in the low temperature phase, but we wanted to study in the middle, what I call the middle T phase. So the propagation vector is this big incommensurate thing, and the kind of interesting thing here is that the polarization is sticking up out of the rotation plane, which classically we wouldn't expect, and I'll just talk about this on the next slide. So a theory like the K&B model, you have a common spin rotation plane shown here. You would expect you had to get the induced polarization is this big load of cross products, so your polarization should be in the plane. And in copper niobium oxide, we find that it's sticking up out of the plane, so it's not even a little bit in the plane. But this sort of theory works for something like MnWO4. So to get around this, Johnson et al. Proposed this ferroaxial model where you kind of you rely on inverse EM interactions. So you say the magnetic structure induces a structural chirality, which then couples to an axial vector. And we're allowed, as we're in one bar, the symmetry can allow an axial vector in any direction, so there's no constraint there. Okay, so I will now move on to talking about the technique that we use. So we use spherical neutron polarimetry, and this is very useful. So, in extension to kind of uniaxial polarimetry, you can analyze all components X, Y, and Z, and this allows you to measure all the components of the magnetic interaction vector. And for example, you can see if you have uniaxial polarization and you get depolarization of the beam, you can, with this technique, you can see if actually depolarization has rotated or if it's actually depolarized. You can also gather phase information between various things. We'll see that a bit more concretely in a minute. So the mathematics behind this, and I'll just go through this briefly. Back in the 60s, so you have your nuclear scattering P's, your magnetic P's. We ignore the nuclear spins, we say they're disordered, and if we take the Born approximation, then we arrive at these things here, and we can compute these in their sort of full tensor of glory, but I'm not going to do that. We go to the standard coordinate system. It's a bit more useful. So we take Rx direction along the scattering vector, and this means that the interaction vector is only in the YZ plane. So we can simplify down these equations, and you can see here. So if we have non-zero propagation vector like we do here, these terms will go away because they have nuclear overlap, so they will go away. And the kind of key ones that we want to look at here are these YZ terms, which remain, and they're quite intrinsically linked to chirality. And you can see here, if we write these things, these are complex things, if you write them in a polar form, you can see how we would arise that sort of phase difference information there. Okay, so I'll just give a short example of where this sort of thing is useful. So if you imagine you have this kind of structure here, where you have these four magnetic atoms, and they order along the z-axis, and you can either say, okay, well, it orders in this way, or maybe it orders in this way. And obviously this way you have these two domains. And if you just used normal unpolarized neutrons, if you had equal parts of these two, you can't tell the difference between the two structures, so you would get confused. But happily, SNP rides to the rescue, and if all we have to do once we calculate the polarization matrix here, we just have to look at this YZ term, and we can immediately distinguish which one we have. So it's really useful for something like this. Okay, so this is the technique that we use. This is the instrument. So this was done at the ILL on the D3 beamline, and we used CryoPad. So you have the setup shown here. So you put your sample in the middle, and you set up some coils and mutators. We'll see a video of this in a minute in motion, and this sort of rotates around, so you can study all the polarization components. So if this will come. So you can see the coil here as I showed in the image. So you have your incoming from here, the reactor is up here, your detector, and this is your sample. And then, so you set up the fields. Okay, so you can see here we've taken up the standard coordinate systems as I did on the previous slide. So once we've set up the instrument, we then have our neutron will come in a minute. Here it comes. So then we can see that through the combination of these two fields, we set it up so that the polarization is along the x-axis here, and then under the scattering process, it develops a y component which we want to measure. So we set up the outgoing fields so that we can identify this y component, this green component, and goes into the detector, and we measure it. So that's kind of how that all comes together. And so CryoPad measures things like this, sort of ratios of spin up minus spin down, and then we can link this back to the polarization matrix, and from this we can refine magnetic structures, which is what we did, and which is what I will now talk about. So we determined the full matrix for many Bragg peaks in both phases, and then used Mactopol, which is some software written by Naveed at the ILL, to refine the structure. And we had to take these constraints. So unless you have nuclear magnetic interference, you're not sensitive to the lengths of the magnetic moments. So we had to constrain them. So here are some results. So this is in the low temperature phase. So if you recall from the start, we have a cycloidal order, and our results agree. You can see the two spins rotate in the same plane, and just as interest, the middle one is out of phase. And this agrees, as I said, with the results. There's about a 7% difference in our rotation planes, but that may be down to the fact that the previous work was powder data and this was a single crystal, so that can account for that. This is the middle temperature phase here. So, and this is the interesting one. So in the low temperature phase, your rotation plane is given by the real and imaginary parts of your interaction vector. And what the refinement found here is that the real part went to 0. So the rotation envelope shrunk down and became elliptical, almost to the point of really elliptical. And you end up with this sort of linear modulation along, which is classically what you would say is a spin density wave. But the issue that this throws up is that copper niobium oxide is an insulator, and a spin density wave, usually you need a nesting vector on a Fermi surface and things like that, which you don't have because it's an insulator. So it raises an interesting question that something must be going on here that we don't fully understand. Okay, so, okay, I've been quick. So just to conclude, so we looked at copper niobium oxide with spherical neutron polarimetry, and we redetermined the magnetic structure in these two phases. And I'd just like to highlight that without spherical neutron polarimetry, this would have been sort of quite difficult, but because we had all the information about all the polarization rotations and stuff, it was relatively simple. And our low temperature data is in agreement with the literature, which gives us confidence in presenting the middle temperature range, even though it's a bit out of the ordinary. So I guess I would like to acknowledge collaborators and funding and say thank you for listening to me.
Very kind.
Yes.
Questions about this talk?
Just a quick question. What is the band gap of the material?
I think it's on the order EV or something like that, 3EV, 30EV, something like that. I can't quite remember off the top of my head. Sorry. Big enough.
For example, in BA4, there is a cycloid in the plane, but out of plane there is a spin density wave in addition to that. And here you are very close. I mean, you have both solutions. So do they coexist sometimes in this system?
I'm not sure if they coexist. I'm not sure what happens on the phase boundary there. We sort of, I guess, looked far away from that coexistence boundary, so they might do. I suspect, yeah, one transforms into the other, so there might be, I don't know.
So what's the sample size?
The crystal was sort of about that big, so I don't know,
So
what,
is it a
centimeter or so.
multi-domain sample then?
No, it was single crystal.
Okay, we thanks again.